Start. Hello everyone, welcome to the video of the Vulture platform computer class computer architecture fall 2017 Harvard Extension School. My name is Rafael Brito and I'm going to explain today the computer that I built for this class. First off, why Vulture? Why not? I think Eagles and Hawks are widely used and overrated, but in reality, I picked the Vulture because it's the mascot of my Brazilian soccer team, Flamengo. So, what is Vulture Platform Computer? Refers VPC is a 32-bit word computer designed and implemented for academic purposes. I provide 32 user registers and 2 protected registers, the IR and PC. The memory is addressable by 16-bit, which is ironic being a 32-bit word computer. But the 16-bit is because of the FPGA Altera DE2115 limitation. And it worked out great because I used the whole immediate field of my instruction to manage the memory. There are 27 instructions, largely inspired by MIPS, and I decided to implement a single finite state machine with a total of 12 states. My intended novel feature was hard interruption, but it was not implemented during the time constraints. Here I give a list of all the registers, pretty straightforward, 32 in total, 0, the 0, and the number 31, the return address. My block diagram, pretty standard again. I have the PC, the memory, the register file, AIU, and a bunch of muxes. And the VPC sequencer is a puppet master for all those components. Here's the list of my states. Pretty straightforward. The only thing that is a little bit awkward is I put 2 states for execute instruction 2, so I gave enough time for my signals to propagate. Execution instruction 2 is actually when all the registers are latched. Here's an example of my instructions. I have the R type. I have 3 registers per line, and all the logical gates. Same stuff. For I type, I have 2 registers on this instruction, and the immediate is a 16-bit field. All the numbers and memory address are 16-bit. My J type, branch, and jump. Some of my compiler directives, I have comments using the standard -- and labels are required before any block of code. Main label is required for every single program. I have the ability for address to map address to a label, and ASCII to inject strings into user data, a memory space. Here's an example of the code, my assembler code, R and some jump and link, load word, and I put a snippet of my principles of operations doc, how for each instruction I documented. My compiler, here's an example when there is an error on the compiler. The compiler first reads the entire file and tries to interpret and gives a total of number of errors. The second part of this slide, when I fix my code and run it again, and then spit out a MIF file. This next screen is the screenshot of my emulator. My emulator, for every VPC instruction, I show this screen, a snapshot of all the registers, and on top the 2 protected registers, the PC, and the IR in 2 forms, the decoded version and in hex. So let's do a demo. I'm gonna do two parts. So I first gonna show the compiler and the emulator. Then on another video, I'm gonna show the actual Altera running, and I'm gonna switch the camera for that second video. So let's do the first video of the assembler and the emulator. So we're gonna show my code. One of the pieces of code that I wrote, the shifter example, I do a bunch of shifter left and right up to 32. I'm just gonna compile this code and I'm gonna do running Java. Then I run it, it's gonna show the MIF file. The interesting about 32-bit that my instruction, I need to read 2 lines of the MIF. MIF lines should get 1 VPC word. Let me show the emulator now. I'm gonna run the final program, practically the final program. That's the emulator. I have an option to dump the memory, but I need to comment it out. But in general, is that every instruction there is this rolling screen with the registers. So I'm gonna put the number here, 56 and 33. Did multiplication, right? Let me now switch the gear for the Altera. I'm going to start a quick demo of the VPC platform computer. I'm going to load the instruction first from the MIF file. What you can see on the screen is a screenshot of the Altera. There's a big lag on the video. I don't know if I'm going to be able to see everything. I'm loading the final program MIF file with all the instructions. Now we're going to commit to the memory, and to restart I'm going to enable the switch to the memory suspend switch. There is no throttle at this moment. I'm going to run 3 interactions of this. First with small numbers. The program put on the screen the number that the user set up. So it put 67, now 567, now it's computing. See, that's a large number, 37,000. Now I'm gonna try with a negative number. Put minus 78. And the second number is gonna be a positive number. The final interaction gonna be with 2 negative numbers. Minus 345 and minus 56. See the positive output. That's the VPC running. Now I'm gonna show some of the switches and buttons of the Vulture platform compute. As you can see, my cheat sheet over here, the computer is running. It's all solid because no throttling. If I start to do throttling, you're gonna see the LEDs. The red ones are the state of my machine, and the green are some of the variables for memory operation. Now I can do the memory suspend using the switch 0. I can go and show my PC over here. I can show my IR. Can show some of my memory address variables. So this is it, the demo, my Altera board. If you're watching this video during the final, we're gonna open now for questions and answers. I'd like to thank the Professor Franco, Mark, and Stephen for all the help during this semester, and I hope to see you next year.